let's briefly look on the agenda of today's training. So the first thing that we will have to learn is what Qt for MCUs package contents are, and what comes with installation of Qt for MCUs. We will go through all subdirectories of installation directory to understand which files are responsible for what and what directories contains. We will build and run application from the command line. This means we will go through the most basic way and the most raw way to compile and transfer your application to the board. This could be useful to fully understand how the build process looks like. Then we will go through the CMake APIs that are quite important thing. If it goes about Qt for MCUs, it provides you multiple ways to optimize your application and organize your application project. Then we will go in detail how Qt for MCUs application build process look like. You will understand how assets are converted, how fonts are then generated, and by which mechanisms your QML files are finally running on your board. And after those topics, we will have a short coffee break to get some rest, and we will get back to training with configuration of Qt Creator, which will lead us to first live coding session, first big live coding session, maybe let's say, in which we will see how to write application in Qt Creator and how to start developing your product. And after that, we'll have another break, which is the bigger one, the lunch break. So it will be the 1 hour one. And after that, we'll learn about assets and how to manage those. And I will follow up this with a live coding session to demonstrate the things we just learned. All right, and shortly about the second day, so about tomorrow's training, you will learn what is different between Qt for MCUs and the big Qt. You will learn how to style the controls like buttons, sliders, toggle buttons, and so on. The coffee break, we will see how to translate our application to different languages, and then, of course, another lunch break, and the C++ integration, which means how to connect your UI to actually C++ code. So how to connect the QML sources with your C++ sources. Of course, in between those, all of those topics, there will be another live coding sessions. So everything you will learn there will be also explained during the live coding session, maybe to have some more visibility how this really look like. All right, software requirements. Well, this presentation was made for Qt for MCUs 1.8, and the 1.9 was released just in a week. So there could be some problems with this presentation as I see right now. So there is a statement that Microsoft Windows 10 is the only supported operating system, but since 1.9, so currently Linux is also supported. macOS support is planned, but we don't know right now when it will be. And well, let me go through the other requirements other than operating systems. So Qt for MCUs, of course, 1.9 for this training. So the most recent one, Qt Creator, CMake, and the MSVC compiler to compile the host and the host version of our Qt for MCUs application, but let me open the Qt maintenance tool to show you exactly what you have to click there to get the proper environment. So after running the Qt maintenance tool or Qt installer, you have to log in, of course. Just click next after providing your credentials, then add or remove components. All right, please make sure that you have selected latest releases on the left side to make sure that the most recent things are visible for you. You can collapse the preview, and from the Qt, you can look into the developer and designer tools, where of course you will have Qt Creator, but it's by default selected. And what can be interesting for us from there, if you can scroll down, there is a CMake, which is the required thing. It's with a higher version that is needed, but it's fine. We will need Ninja to accelerate our CMake processing. And this is it from the tools, I think, from the big Qt. And then we can go to Qt for MCUs. Right, there is Qt for MCUs 1.9. And from there, we will need desktop MSVC. If you will expand this, and there's only a monotype Spark, which is selected by default. And for this training, this is the STM one. We will use STM32F769i discovery board. So you have to select the exactly this one for Qt for MCUs with a support for that board. Under this section, under this board, and as well under other boards that you can install, of course, you can install demo binaries, the compiler toolchain. I have both of them, so so the RNGCC and the IRR. And there is also a monotype Spark support. Let's collapse this. So from Qt for MCUs 1.9, you will need the desktop version and the STM32F769 Disco. And probably there's a question. There's no. Well, if I understand the question correctly, so you do not have the Linux host installation in the installer, and can you do anything about this? Well, you should have that. If you are running the Qt installer on the Linux host, you should have this option enabled. Just make sure that you have the latest releases and the Qt for MCUs 1.9. Right, from the Qt for MCUs section and the third-party tools and SDKs, what could be interesting for us is, of course, RNGCC 9, which is also installed together with the package here. And as we are using STM board, STMcube programmer, and STM32Cube F7 SDK, those are the things that are needed for this training if we are going to work with exactly this board. Of course, if you are going to use different board, you probably will need different SDK. All right, and this is it if it goes about Qt installation. So I will just click a cancel. If you are going to install anything, you of course have to click next. All right, and another thing is to configure the MSVC compiler for the Windows, as this training is based on the Windows operating system. I will demonstrate you how to run Visual Studio installer and which things are needed from there. There is a question from Claudio, why I selected two versions of ARM GCC C++ from ARM C++ GCC. Well, let's say this is just because I have previously configured my environment for the Qt FreeRTOS 1.8, and this was delivered with the older version, and right now 1.9 is delivered with the newer one, so I just have both installed because I have the previous one still present on my device. But normally you will just need the one. All right. Well, so this is a Visual Studio installer. And let's see what do you need from there. So on the example of Visual Studio Professional in 2019, let's click Modify and Individual Components. And right now you will have to select two things, MSVC and MSVC. And let's search for the proper ones. So MSVC version 1.4.2, of course, for the correct architecture, 32 and 64 bits. And another thing is to install Windows 10 SDK. And just type Windows 10 in the search bar, and let's select the most recent one. And that's it. You just have to install those two things. If you're curious what could be needed as well, you can think about documentation, which is available online. Of course, it's also delivered as an offline version, but probably the most convenient thing will be to use that online. It's under doc.qt.io/qt4mcus. All right, this is it if it goes about software requirements. And right now, let's see what you are receiving after installation of Qt FreeRTOS. Of course, you will receive Qt Ultralite graphics runtime, Quick Ultralite graphics runtime, which is the heart and core of Qt FreeRTOS. This means this is the part that is common for all Qt FreeRTOS ports. If you are working, for example, with different STM boards, they will have a bit different platform adaptations, but they will have the same Quick Ultralite graphics runtime. This is the thing that is calculating all of the UI elements, positions, sizes, and it decides which parts of the screen needs update. And this calculates all of the animations, controls all the mechanics that is driving the whole Qt FreeRTOS. You will receive Qt Quick Controls library, which is a subset of Qt Quick Controls that you can know from the Big Qt. It also comes with default styles for them, and the mechanisms to provide theming, so you can override the default styles and provide your own. I mentioned that a bit before. Platform adaptation libraries that are the adaptations for particular hardware. Those platform adaptation libraries are then linked together with Quick Ultralite graphics runtime to provide rendering acceleration. If, for example, your device will have a GPU, and the platform adaptation will will take care about transferring all the rendering requests from the Quick Ultralite graphics runtime to finally to the hardware. And the platform adaptation is every time different for every hardware you will have. So for example, different STM boards, you will have different platform adaptation libraries, and that accelerates your rendering in the most efficient way. You will receive development tools, which means Qt Creator with integration for it, and for example, the linguist tool to provide localization support. We will learn about those two during the live coding sessions. Offline documentation and examples with the source code is also delivered together with the package. And there is a question: can we have MSVC installed from this was the 2017 version? From my experience, yes, it should work. Simply, it should work. All right. And the folder structure. So let me right now prepare for it. I will open the installation directory. All right, here it is. So this is the main Qt installation directory. Okay, there is a question. I can confirm this is how I've installed it. Okay, perfect. Thank you very much. All right. So this is the main Qt installation directory, and let's review what is important for us and for Qt for MCUs. And before I will start talking about Qt for MCUs package itself, let's look on the tools that we have also installed. So in the main Qt installation directory, let's search for the tools folder. Let's go inside. And the things that are important for us here is, of course, CMake, which is installed directly there. And Ninja tool is also installed here. And for example, Qt Creator is also in this directory. And there is also Qt MCUs subdirectory, which contains the things that are specific only for Qt for MCUs. And as you can see, this is the ARM-GCC directory with two versions, as one of you spotted during the previous environment setup, but only the one will be used. So in my case, the ARM-GCC 9. And for different vendors, there are also different tools that are installed together, or the SDKs, as in this case, for example, STMcube SDK for the F7 family is installed here, and Cube Programmer installer is also located in this directory. Let's get back to the main installation directory, and let's review Qt MCUs, which contains all versions of your Qt for MCUs installation. 1.8 is well, almost empty in my case, as I uninstalled this one before this training. We will use 1.9, which contains a lot of things. And let's review each of those directories. What are they important for? Why mean GW compiler is installed? It's currently not related to Qt for MCUs. It's also a thing that is related to my environment setup that was needed for the big Qt. And for different purposes done for Qt for MCUs. We are planning to add MinWG, MinGW support for Qt for MCUs, but we do not know when this will happen. But there is a plan to replace MSVC with this one in the future. But as I said, this is not related to Qt for MCUs right now. All right. Well, then let's review what comes exactly with installation of Qt for MCUs. So there is a bin directory which contains tools that are needed to compile your Qt for MCUs application. Those tools are responsible for example, converting QML code to C++. This is responsible as well for converting the assets and for generating the fonts, the glyphs, and so on. And also this directory contains some libraries from the big Qt that are needed to run your application on host machine. So you do not have to install the big Qt. You will just have to use those libraries that are located in this bin directory. And then you will be able to run your application on the host machine without flashing it each time you will change your UI. Compatibility directory contains some convenience implementation for some types that are not available in the big Qt, and those compatibility modules are, for example, for Qt Design Studio to provide you compatibility between the Qt for MCUs and big Qt. So if you have your application written for Qt for MCUs and you are using exclusive types there, then by using this compatibility module, you can, without any problems, run your application on the big Qt as well. Demo images, as the name indicates, contains images, precompiled images of demos for both bare metal and the FreeRTOS. And those are just simply demos that are ready for flashing on your device. And for each device you installed, you will have another set of precompiled binaries that you can immediately flash to your devices to test out how the things are working on this. Demos directory contains simply sources for those precompiled images, so you can compile those by yourself, or you can just look how the things were built. Docs, of course, documentation, but offline. Examples contains sources for simple applications. Well, for examples, as the name indicates as well. Those are small applications which presents particular features. You can see how particular features were used in more atomic way, and those are sources for those small applications that demonstrates some of the features. Include, of course, contains headers that are needed to compile the things properly. Kits are the files that are used by for example, Qt Creator. And kits defines what tools you have to use to compile your application for a particular target. And for example, in our case, if we are going to use ARM GCC for STM32F769i discovery for bare metal, we will use this kit, which is simply a JSON. And in this kit, we have a definition of the compiler, of the SDK, vendor, type of the board, and so on. The lib directory contains all of the Qt for MCUs libraries that are precompiled, and in this directory you will find all the parts of Qt for MCUs precompiled to static libraries. This means this is the Quick Ultralite engine. This is the platform adaptation. This is, for example, the monotype Spark integration, some charts, and so on. If you are going to use the PNG decoding, there is also a separate library for it, and this directory contains all of those. The platform subdirectory contains some specific code for the platform. So for something what is specific to the particular hardware. And for example, for F769i discovery bare metal, we have some different CMake configuration. We have the common directory for F7699 discovery, which contains some platform adaptation, and you can clearly see how the platform is built and how the platform is transferring all of the rendering to the hardware components. And then you are just sure that your implementation and Qt for MCUs implementation is doing exactly what you need. And if there is a need to modify this platform, for example, to support different LCD, this is also a place probably where you will search for custom modifications. Plugins, so those are additional plugins for tools which provides support, for example, for different image formats. Source contains additional files that are typically shared between applications. For example, some third-party sources for monotype, or some common parts like default main entry function implementations that can be used in your application to speed up the prototyping process, for example. And util contains some utility files that are used by tooling around. All right, so this is about Qt for MCUs installation directory, and those are the things that are installed together with Qt for MCUs. I mentioned about this a bit before, and there's a thing that we call desktop backend, and this is a thing that is really useful in Qt for MCUs. Provides you a way to run your application on host machine. So if you are, as in my case, developing application using the Windows 10, you can run your application on Windows 10. And this uses the big Qt to render the things, your controls, images on the application window. And this is made to speed up the things simply. By running your application after you modify your QML files on the host machine, you are saving a lot of time. You will see in the next live coding sessions how application size and how application assets are causing longer and longer time of flashing our application to the target board. So to save some time, if you are just developing, for example, a single feature, to verify that alignment of some elements is proper, and then, for example, you can check for the colors and the assets and so on. You can do all of those things on the host, and then just verify, for example, the performance on the final hardware. And trust me, this is a much faster way of doing that, and this will be clearly visible during the live coding sessions. Of course, it currently uses MSVC compiler on the Windows. I mentioned that before, that there is a plan to transfer to MinGW in the future, but we don't know how. We don't know when it will happen finally. All right, so this is a time for creating the first application, and I will do that during the live coding session. And you will learn how to set up your CMake project. And in this part, you will see how to use command line to build your app, and then how to use the command line to run your app. And simply, let's get started with it. I'll prepare for it. All right, so I will open the terminal window. I will use the commander, but it can be any different one. So you can also use the default CMD from the Windows. This is not important thing here. And as you can see, currently I'm in some directory that is prepared for this training. Let's review the contents. I have some training materials. Oh, well, maybe this is the important thing. So currently you don't need that for this live coding session, but you will need some training materials in the further live coding sessions if you are going to follow those with me. And well, maybe I will try to share those with you. All right, my friend just write me that he will do that for us. So Jakub will share with you some training materials. I will explain you how those works in the next live coding session. And right now you don't need those, so you can follow these steps with me by just typing the same things on your side. So let's start. As I reviewed the training directory, there is also one with training materials that are going to be shared with you. And right now I'm creating the directory to keep all of the things of our first minimal application in the separate place. So make directory, first up. And let's go inside. And I will right now create a first QML file which will define UI for our application. And I will use Visual Studio Code for it. And again, you can use anything what is more efficient for you. So code main.qml. This will open up a new window of Visual Studio Code. And let's try to define some UI. We will need import Qt Quick subset of the types. And I have to mention that the version in import is optional. Right now, I will just type it to be compliant with the next live coding sessions. Normally, it's not needed for Qt for MCUs, but it's needed for Qt Creator tool, for example, which will force you to provide this. And Qt Creator will need that to understand your imports, but Qt for MCUs will skip the version and always it will use the same, most recent one. So you just have to know that. All right, so we have import of the Qt Quick. Okay, but before we continue, there is a question. Why I'm using Visual Studio instead of Qt Creator? Well, so Visual Studio Code for this step is the more lightweight version, and in the next steps I will use Qt Creator. So just to not provide anything overcomplicated, it's just the most simple way to write the file. Qt Creator is a bit bigger tool, I think, so it's easier for me right now to use Visual Studio Code instead of Qt Creator. But as I said, in the next steps, I will use Qt Creator, and this is the only live coding session that uses something different. Right, let's continue with defining the UI, and I will create our app, the really simple one. So I would like to have the whole screen or whole app filled with the single color. So I will use rectangle as a root of our application, and I will provide some specific color for it, magenta. Right, let's save the file. Okay, and right now we will need the CMake file to define how to build our application. All right, once again, I will use the code for it. And I'm creating the file cmakelists.txt. Okay, we are redirected to Visual Studio Code, and right now we can start defining our application project. First thing, CMake minimum required conversion. This is not that important at this step. We have to define the project. Let's call it first up. First up. Oh well, there was a typo. And we will use C++. We need to find the Qt for MCUs package, and in CMake APIs, it's called QUL. So we have to find package QUL, right? So we have CMake minimum required version, we have a project defined, we have a package found. The next thing is to add the target to compile QUL, and this is the first place where we are using the QUL specific macros. And this is a Qt add target. It defines the compilation target for your application, and also it has a possibility to compile your app as a static library, but we are not covering that right now. I will talk about this later on. So we are creating a target first app, and right now we have to tie up the QML file with our project and with our target, and there is another QUL function for it, QUL target QML sources. And for the first app, we are adding main.qml. All right. And at this point, we have almost everything defined, and you can wonder where is the main entry point for our application. And there are two ways of doing that. We can define this by our own, by just creating another C++ file, and by defining the main function there and running few functions to just initialize Qt for MCUs, and then we can start executing our application. But the most simple way of doing that on the first step is to use one of the predefined main entry points. And we can do that by using one of the Qt for MCUs macros as well. And this is app target default entry point. And this entry point is for target first app, and we have to provide the root QML file for our application. And in our case, it's the main, and we are providing that without the QML extension. Probably some of you just spotted that I used some macros that are starting with a QUL, and this one is starting with an app. And this is not a mistake. This is by design. So all of the QUL, prefixed macros are the things that are crucial for Qt for MCUs project, and all of the app, all of those macros that are starting with app are the optional things that can be just simply removed and replaced with your own implementation without any problems. So just to make it more visible, those optional are starting with app, and those required are starting with QUL. And you probably it won't be probably that easy with removing those needed. Let's save the file, and right now we have everything ready to compile our application. Let's get back to terminal, and I will create another directory for build. Let's review what do we have here. Okay, we have both files just. Well, okay. So I will define right now some environment variables maybe before creating a build directory. So first of all, we need to we need some environment variable that will tell where the Qt Frames installation directory is. And to do this, we are defining qul_dir, which will point to Qt root direction. This will point to Qt root installation directory, then Qt MCUs and the version, which is 1.9 in our case. All right, and we need CMake. So let's verify if we have any. We do not. So let's extend the path to make it visible for the terminal. Set path. Preserve the previous path. Semicolon. All right, and we will use the CMake, which is delivered together with Qt installation. Tools, CMake, in. All right, let's verify. And we have CMake visible right now. So let's try to generate the build target and let's build the application for the host machine. I create directory for desktop. I'm going to that directory and let's trigger CMake for the parent directory with the platform, Q platform. This Q platform variable is defining for which platform we are compiling our application. And for the host, it's just a Qt, as it's based on the big Qt. Let's provide architecture x64, and let's try to run. All right, so we have our application target generated properly. So right now we can try to build our application. And to do this, we are also using CMake, build this directory for target first, up, and for the release. Okay, there is a typo, not blue, not build. All right, so application is right now built properly. Let's try to run. And it's not running. It's a correct behavior right now. And I'm going to explain you why. So right now, there is system has reported that it cannot find the Qt libraries that are needed to run our application. And those libraries are exactly those which I showed you before during the installation directory review. And we have to extend the path with a directory that holds those libraries to make system able to find those libraries. And this is the normal way of doing this in the on the Windows. So let's extend the path. Let's extend the path by once again preserving the previous content of it, semicolon, and qul_dir, which we have defined before. All right, let's verify. And perfect, we have our application running on the host machine, and it's exactly how we defined it. It's a rectangle with a magenta color. And there is some message on the chat. Okay. All right, now Jakub has sent the materials for you, but I think for panelists, so I will just resend it for attendees as well. Okay, thank you, Jakub, for sharing the materials with us. And right now you should be able to download those from the Dropbox, and the link should be visible for you on the chat. So just please download those in the meantime. this could be needed in the later live coding sessions. There is a question: can you show 2 path variables you added again? Sure. So this is the first one. So maybe let's copy this. I will send you those in the answer to your question. So this is the first one. And this is the second one. And there was only those 2, I think. All right, so I'm sending you those 2 path variables as an answer to your question in the Q&A section. So you should be able to copy those on your environment. All right, so this was for the host, and right now we will try to run it on the real hardware. And please notice that I won't modify anything in our application project and sources. Let's get back to the root directory, and let's create another build directory for STM board. Let's go inside. Perfect. And what do we have right now? So compilation for the hardware is a bit different. So we will need additional environment setup for it. And first of all, we have to define ARM/GCC toolchain directory, ARM/GCC build. It's also delivered with Qt installations, so we will point this to C Qt tools, Qt MCUs, ARM/GCC 9, right? And we will extend the path once again with the path to the Ninja by preserving the previous path. And let's point this to Ninja that also comes with Qt tools Ninja. All right, let's verify that Ninja works. Perfect. Okay, there is another question. What does exactly Ninja do? So this is a generator for the CMake. Well, it does the processing of the files during the compilation, and it also provides you a way to compile your application in the faster way, as it supports, for example, the multi-threaded compilation. So this is just a bit of a help for us to simplify the command line commands. It's an improvement for compilation time. Well, simply those 2 things are most important things, I think, right now. You will see how triggering a build is different in a minute. But in general, you can live without the Ninja. It's not mandatory thing. It's just for the training purposes to demonstrate that you can use this with Qt for MCUs. All right, so we are in the STM build directory. We have the environment setup. So right now, let's generate targets for STM board. And I'm triggering a CMake for the parent directory, so for our application. We are providing Q platform, which right now will be different as we are using a board, not the host right now. So STM32F769i dash discovery dash bare metal. And let's notice that we are providing also the operating system there. Well, in this case, no operating system as it's a bare metal, but If you're, for example, going to use the FreeRTOS or any other operating system, you will then provide this in your Qt platform. Let's define the release build, CMake build type release. All right, we have to tell that we are going to use different compiler. So we have to provide a toolchain file for the CMake. CMake toolchain file. All right, and those toolchain files for particular compilers are delivered together with Qt for MCUs. So you just have to point this from the Qt for MCUs installation directory, and we will use our qdir environment variable that we have defined before. And toolchains are located in lib CMake toolchain, and this is called arm gcc CMake. All right, and let's tell CMake that we are going to use Ninja as a generator for the targets, and that should be it. Let's verify if everything is fine. All right, it seems it is. So you can review the output right now. So toolchain was detected properly, and CMake has verified the compiler also properly. There is a qdir which points exactly to our Qt for MCUs installation directory. So it seems that we are ready for compilation of our application. And to do this, as we are using Ninja right now, it's more simple than previously. We do not have to provide that full long command to tell that we are going to build this directory and then selecting the target with different arguments. We just have to call Ninja with our target, Ninja first, and that's it. We have to just wait a bit. And here it is. So the whole compilation is more tightly coupled with 2 lines. We also do not have that full log of a build. So this is another thing that Ninja can be used for. But well, let's get back to the topic. Well, so currently we have built our application, but you can wonder how to transfer this application to your device using the Qt for MCUs, but because this is possible. Before I will do that, I will just show you what is currently on the device by sharing with you view from the secondary camera. So, well, you can see right now this is my hand, so this is not the recording. Okay, there is a question, maybe let's answer this. We've mentioned it at the beginning, but I want to be sure. Must I know QML to use Qt for MCUs? Well, yes. QML is the way that QML is the way how you define the UI for your application in Qt for MCUs. So you have to know that. But during those live coding sessions, I will show you everything step by step. So if you are going to follow me on live coding sessions, it will be enough. You probably won't have to know that much, but in general, if you are going to develop the application, then you have to know QML. Right. So just to show you that right now application is the board right now is just showing the some content from the memory. This is anything that is useful for us. This is just some garbage that is located in the place that the board is expecting to have the frame buffer for the LCD, and we are going to change that. Let's get back to sharing the screen. And to transfer our application to the hardware, I just have to call one of the flash targets that are prepared by Qt for MCUs. And this looks like this: Ninja flash underscore first up. And this target is added automatically if you have installed the Qt programmer during the environment setup. Qt for MCUs automatically detects that you have installed the programmer for the board and creates additional flash target for you, which does all of the things for you implicitly. You do not have to worry about how to transfer your application and your binary to the board. And right now I'm going just click enter, and I will switch view to secondary camera once more to show you that application has been transferred to the hardware. So I'm just hitting the enter, and I'm switching the view to the secondary camera. So still, this is my hand. This is not the video. Let's wait a bit. Application will start flashing in a second. You can see maybe that the LED near the cable were flashing for a while, and here it is. And this is our, well, let's trust me. I always have to say that the camera is not the best quality, so you probably can see the blue screen, but trust me, it's the magenta one on my side. So our application is right now transferred exactly in the way we have defined it to the board by just calling one target from the CMake. And you can review the output from the flashing, how this was looking while I was showing you the secondary camera. So there is some output from STM32Cube programmer, and there is some progress of downloading your application. So even if you will encounter any problems, you will be able to review what is exactly the problem on your side by reviewing this output. Do you have any questions to this part, to the compilation of our application in the command line? Maybe you are still missing some environment setup, some paths and some environment variables. Is it possible to use STMicroelectronics programmer to transfer to the file to MCU? Yes, just as I said before, Qt for MCUs is using STMicroelectronics programmer under the hood to transfer this application. It just covers STMicroelectronics programmer it covers it in this flash target. As you can see, I just run this flash underscore first up target, and under the hood, this target is running the STMicroelectronics programmer to flash our board. Even if you are looking carefully, there is an output from the STMicroelectronics programmer. So in general, it's using it. You can also, of course, you can also use this by your own, but it will be a bit harder, I think. Well, I can even show you that there is. Well, let's open the first up build STM directory release, and here you can find the ELF and the hex files that you can also use by your own to flash the board with STMicroelectronics programmer. But well, I'm not sure if you are going to do this as a first step, as just using the Ninja flash target is a simpler thing. I also see that Jakub is pasting some answer for you, so just let's wait a bit for him, and probably everything will be more clear then. And let me go further with our presentation. So this is the end of the first live coding session, and let's sum up those things. So to configure your command line setup, you have to, of course, create a separate directory for for your application, where you will hold your QML files and the CMake configuration. You have to define the QDIR environment variable to tell your operating system and Qt Frames use where the files from Qt Frames use are located. To compile the things for the host, you have to create a separate directory for the build. Then you are triggering the CMake with Qt platform Qt, and this will generate your targets to compile your app for the host machine. You can, of course, trigger it with that typical CMake syntax for compilation. And to run your app, you have to tell your operating system where the Qt dynamic libraries are located in your installation by extending the path with that directory, and then you can run your app by just simply running the exe file, which is the result of compilation. For the hardware, of course, there is just a need to define the variable for the toolchain, for the compiler that you are going to use with it. And then you can also generate CMake targets, compile it, and flash the board by using our flash targets, or by your own way. It's also possible to flash the ELF files separately with your own solution. Well, we were using some CMake APIs during the first live coding session, but those were not explained, and those were rather only a few of them. So let's right now focus on those and on different CMake APIs and what those are doing for your app and for us. So first of all, the Qt platform argument for the CMake, it holds the target platform. It defines for which board you are going to compile your application, and this is causing that finally the app will be linked with a different backend. So for the STM32F769i, it will have a different platform backend linked than for Qt, which is also a default thing. And by switching this value, you are simply switching the platform that is your target for the particular compilation. Qt color depth is defining the target color depth for the display, and this must be one of the 8, 16, 24, or 32 values. And well, in the most cases, it also defines the frame buffer format. So by lowering the value of this parameter, you are also lowering the amount of memory that is allocated for the frame buffer. But some of the platforms that are supporting the hardware layers are using this value just as a default value for the layer, as this can be overridden in the QML then. QLab target macro is a thing that we were using in our first application. Okay, there is a question, so let's pause. Is it possible to run on the FreeRTOS instead of bare metal just by changing the target? Yes, it's possible. It's exactly how it's done. You are just changing the platform to STM32F769i -discovery-FreeRTOS, and that's it. You just have to recompile your app. Any more steps are needed. All right, so QLab target defines the target for your application, and also it defines what your application has to link. So it automatically links Qt Quick Ultralite libraries to your target, and also it provides you a way to create a static library instead of the binary. This can be useful if you are going to create the big application, big environment, so maybe ecosystem, and Qt Frames use in this ecosystem is going to be just a module. Then you can use that static library flag to just compile your application as another library that you will link finally to your big app. but this is the more advanced thing probably. Some example is below. So how to define the example app with two sources? Well, it also supports providing the C++ sources. What would happen in the case? There is a question. What would happen in a case the color depth configure is not supported by the hardware? Typically, it will cause the compilation error, so you will be informed. So this is simple as it. And well, for the platforms that are supporting the layers, it will fall back to the closest possible. But this is something that will be clearly visible in the platform sources, so you can always verify. What will happen for such platforms, but normally it will cause the compilation error for these simple boards, and for the more advanced with a layers support. Well, there will be a fallback to the closest. How to add the QML files to your project? There is a macro Q target QML sources. You're providing the target from the CMake and the list of the QML files that you are going to add to your application. It also supports some optional arguments like output directory. And this will mean this will change the default directory in which the artifacts for the compilation will be held. You can use, well, you shouldn't use that. There is a module URI argument, which is a deprecated API to define the modules. This is the old way and shouldn't be longer used. And there is also a copy QML files optional arguments, which will tell our build process to copy source QML files to the output directory. This can be useful if you are going to use your QML files in some modules. Application entry points. So those are those utility, maybe not utility, convenience macros that you can use to speed up the development process, some prototyping process. You can define default entry point by just calling one of those, or both of them in the same time. App target default entry point defines default entry point for your target. And also it takes an additional argument with root item, which defines the root QML file for your whole application. And this will depend on the OS which is selected. If you're compiling for a different FreeRTOS and for the bare metal, this macro will does something a bit different. As for the FreeRTOS, it will pick a different entry point, which will also initialize the FreeRTOS things next to the Qt for MCUs. And app target setup OS is convenience macro to define your operating system in the CMake, and it will then set up some allocators and so on for your app. Previously, I said that there was a deprecated API for defining the modules, and this is the modern and the current way of doing this. There is a separate macro for it. Qt add QML module for the target, which will be a separate target for your module, of course. Defines the separate static library that will hold your module separately. And let's review the arguments. URI will define the URI, which will be then used in other QML files to import your module. List of QML files, of course, to define your module things inside. The headers, if there are any. Sources, if there are any. You can also provide the imports that your module is that your module requires, and output directory to redirect the compilation artifacts. It's also the important macro, as it's a required thing to define the singletons. So if you are going to create a singleton in the QML that you would like to have in your whole application, then you have to use that that macro to define that singletons. Qt add resource is a macro for adding assets. If you are going to add some images, you are going to use this macro. And how this looks like, it just picks, of course, the target, list of the files. There are two optional arguments prefixed in the base to manipulate how you reference your files then in the QML, but I will cover those later on during the resource topic explanation. Of course, the output directory can be changed by providing a different path. For translations, there is a one macro, Qt target embed translations. This define translation for your target, and also it creates some additional CMake targets to generate missing translations, but this also will be covered later on more in detail during the topic of translating your application. And finally, to integrate your application with the C++, you are going to use Qt target generate interfaces, and this macro is taking of course the target and the source files, which are typically the headers that holds the definition of C++ classes that are then converted to the QML interfaces, and this provides you a way to connect the QML and the C++ together. Some properties related to fonts. There is a Qt fonts dir. This simply defines where the fonts that you are going to use are located. By default, it points to source third-party fonts subdirectory. If we are moving from the Qt FreeRTOS installation directory, and Qt default font family defines the default font family for the whole application. And by using this argument, you're able to change the fonts for whole application globally instead of modifying each font.family property for text or the static text components. By default, it's a deja vu sans. Some resource-related properties. The Qt texture cache, it's the really important property, and we have to focus right now. So this defines the maximum image cache size in bytes. It also has to be set before calling add executable. And why it's needed and why it's important and what it does. So there is a concept of image cache, and it's used for multiple things, but let's focus on some example. If you are going to use compressed images in your application, so you are flashing your application with assets in the compressed format, for example, as a PNGs. Then during the rendering, you have to decompress those images for some time. At least for time of blending or bleeding this image to the frame buffer, and some space has to be prepared to keep that uncompressed image for a while. And this is what image cache does. It just holds some space for such dynamic cases where you have to or would like to decompress something or put something to cache for the faster access. And we are, by providing the Qt texture cache property, defining how big that image cache is. And it must be set to at least the size of the biggest decompressed image to be cached. It's because If it will be lower, then that image cannot be decompressed properly, and your application will just halt. And from the other side, if you will set this value to big one, you can overlap some other things in the memory, and well, the behavior will be undefined. And so this has to be used with special care, and we have to keep in mind that the value, the size of the texture cache has to be at least of the size of the biggest decompressed image, but it cannot be too high to prevent some malfunction of your application. There are some additional CMake options for debugging, so you can enable bytecode debugging by enabling the QL debug bytecode. It will generate the JavaScript bytecode for the QML functions and as a comment to the right side of the code. Also, there is a QL debug line directives, and if you will enable that one, it will generate the line directives, which will point back to QML source. So if you are then debugging your application, your debugger will be redirected to the QML files instead of the C++ files to see where you are exactly in your UI code. By default, is disabled, and the line directives are generated as comments. So still, if you are not using it, you can review and point back manually to some QML lines. All right. So this is about the CMake APIs, and right now we are moving to the Qt for MCUs build process. And this is a quite complicated thing, but we'll try to explain all of those things to make sure that every of us understands how particular steps look like and what are responsible for. So we will be going on this diagram from the top left corner to the bottom of it. So the first thing that will happen is, of course, the root CMake list.txt file, which defines your CMake project at all. So everything that will happen with your application in the compilation process is defined in your CMake lists.txt. And well, the next step is to compile the images, if there are any, for your application. So if you have any assets in your app, they will be prepared by the tool called QLRCC. And what it will do with those assets, it will convert those assets to the binary form, to the bitmaps, or to the compressed formats known by Qt for MCUs. Depends on what are your needs defined in the CMake lists.txt. Those bitmaps will be just the C++ files with normal arrays with a bytes, which will be then added to the compilation. And the next step is to compile the fonts. So the Qt font compiler will go through all of your QML files, will take your font file and will generate the fonts as alpha maps. So in general, as a bitmaps as well, but in the alpha formats that will hold just the transparency for the pixels to save some memory. But in general, Qt font compiler is the second step of compilation. It will generate the glyphs for the text that is used in your app. So it will only generate the glyphs for characters that are really used in your app. You can, of course, extend the range of the glyphs by using some other mechanics, but we'll cover that later on. The third step is to generate interfaces, and it's done by QL interface generator tool. It takes the headers, the C++ headers of C++ classes, and it translates those C++ classes to the QML files, to the intermediate QML files that are then passed to the next step together with your QML files. So your UI definition that is held in your application directory together with those intermediate QML files for interfaces to connect your C++ with QML are going together to Qt CPP tool, which converts all of the QML code to C++. So finally, you are not running QML interpreter on your hardware. You are just running the C++ code, which is the much faster thing for the microcontrollers. And finally, all of those auto-generated C++ files. So the bitmaps with the arrays of the bytes for the images, for the fonts, the C++ files after QML conversion, together with your C++ files, are compiled and linked to final binary. So this is how Qt FreeRTOS prepares and then compiles all of the things for the host. Does that mean that indirectly header files are converted to CPP? I'm guessing that you are talking about the part of QL interface generator. No, it does not mean that. Those header files in the step QL interface generator, those header files are converted to the intermediate QML files, but QML to CPP is able to detect that those are QML files that are intermediate, and it will not generate additional C++ files for those. It will use your C++ implementation for those headers. So this is just to make Qt to CPP, let's say, happy, and to tell that those QML types are going to be implemented by developer of the application. So there is no indirect conversion of headers to C++. All right. Well, so this was in overall how the build process looked like, and right now let's focus on the tools itself. QLRCC is let's get back. QLRCC is a tool to convert the images to C++. As I said, it follows desired policies. So if you are going to have images in the compressed format on your hardware, it will just recompress those to the formats known by Qt FreeRTOS. It will also follow desired resource loading policy. So it will hold the information if your image is to be read from flash or it has to be copied to RAM. It can optimize the image for graphical transformation. It will generate the C++ as an output with a C++ byte array, and depends on the compression. It can be a compressed byte array, or it can be a normal bitmap of a given format. It also has a pretty good way of optimization of semi-transparent images. Let's imagine the case where you are, for example, displaying some gouges, so rounded gouges that are mostly the frames, and let's say 80% of the image is completely transparent. And this tool is able to cut that parts and compose your image with a smaller pieces of it to save some memory for you. QL Font Compiler is a tool responsible, as I said also before, it's responsible for converting the fonts to C++ byte representation. It generates the glyphs and stores that arrays as pre-rendered alpha maps. It will also detect how and which glyphs are used in your application, and will generate glyphs only for those characters that are used in your app. You can overwrite and extend the range that is used to generate glyphs. So you have the full control of what this tool generates for you. QML interface generator is a thing to generate interfaces from the C++ to QML. This will be covered in detail. Really in detail tomorrow. But in general, this is the way of generating the interfaces to connect your QML with your C++. For example, if you are going to get some input from the user, and based on that input, you are going to trigger some hardware. For example, I don't know, connect to the Wi-Fi or trigger some pump or something. So then you can connect your QML and transfer those events to the C++, and based on that you can from the C++ manipulate some hardware by calling some BSP functions. And well, there is a question: are all the resources, images, fonts loaded at the same time as the executable, or they are lazy loaded? Oh well, so this can be done as you wish in general. So if by default all of the assets are just located on the flash. So during the rendering, the GPU or some accelerator is just reading the pixels of those images, fonts, and so on from the flash. And if you are going to load this to the RAM, you can also define that. You can tell Qt for MCUs that hey, listen, I'm going to have those files in the RAM, and Qt for MCUs will load those images during the startup to the RAM, but only those that you are selecting for this. The other way is that they are lazy loaded. For example, if you are going to use compression, so if your images are compressed, then they will be loaded and decompressed in the lazy way. So this depends on the properties that you are setting on your images. So normally this is not loaded at all. It's just lying on the flash, and it's read it directly from there. And you can decide if you are going to load those on the startup to the RAM. And if you have the compressed format of the images, they are then lazy loaded to the image cache. And once the image cache is full, it will free some old resources from there and will load again the most recent files for you. Just let me know if that answers your question fully. Well, so getting back to QML interface generator, well, it's used basically to convert the header files of C++ classes to QML intermediate files for the compilation process, and forwards all of the properties, signals, and functions to QML. So if your class contains properties, signals, or the functions, it will be transferred to QML and will be accessible from the QML as well. QML to CPP, simply it converts every QML file to CPP. It also adds some initialization code to your app. So your C++, your intermediate auto-generated C++ files are ready to go. They are transparent for you. All the initialization and stuff required to allocate your classes is also generated, so you don't have to care about those. Well, and as I said, it's also smart enough to detect which QML files are the QML files that are intermediate for the interfaces, and then it does not create any C++ sources for it. It just uses those to understand the relation between some QML components. Well, there is a question. Does QML understand C++ stuff? For example, functions that return unique or shared pointers. Well, not that much. So QML will understand some basic types, and I will also cover that in the part that will cover the whole C++ integration with the QML. But basically, it just understands the most basic types like a bool, integer, some floating types. You can also return other complex types, but those has also to be interfaces that are exported. So in general, you can mimic some behaviors, but not all of the types are supported. For sure, the unique or the shared pointer won't be supported out of the box. Well, so this is about QML to CPP. Well, just maybe let's agree on the simple rule. If my answer is really answering your question, just please let me know. So I'm sure that there is nothing more that you're interested in. And if there are still some unclear things after my answer, just let me know in the Q&A section by adding additional question for it. Then we will be sure that we are not missing anything there. Sometimes it's hard for me to understand the question fully. Maybe it will be easier for us to get some feedback. So just please let's agree on that. If my answer is answering your question, let me know in Q&A section that okay, it's fine, or just let me know it's not enough for you, and we'll try to dig in more. Thank you very much. So, well, let's go further with the presentation, and this is the time for coffee break. So just before we go to the coffee break, there is a time for additional questions, maybe to the some previous parts of this training. Some things maybe are still unclear and or in your head. So this is a moment for clarifying that. In the meantime, I will prepare timer for 15 minutes. I will wait a bit for maybe possible questions. All right, I don't see any. So let's see each other in 15 minutes.